Okay, so welcome to our systems engineering course. Today we're going to cover chapter 4 on the activities of preliminary systems design, which means system design in a preliminary fashion, but still at the system level. In chapter 3 we covered the conceptual system design and the elements of that. So here we're just going to take care of or refine the aspects of system design. So it's going to be more detailed, but it's still at the system level. So some specifics of what that is. So we're going to do a lot of the same things that we discussed as applicable to the subsystem elements of the overall system. We're also going to talk about more types of specifications for processes and materials beyond the type A that we already discussed. And just like we did functional analysis and allocation during the conceptual system design, we're going to do that also for all the subsystem levels. And through the additional specifications that we're going to discuss, we're going to be able to set up the baselines for more detailed design that we're going to discuss in chapter 5. Keeping in mind that even the more detailed design, the activities that we're going to discuss in chapter 5 are still at the system level. So they don't really entail the detailed design of the components and the actual coding of the software. It's just the preparation for these activities. And then we're going to wrap up the chapter talking about how these activities put you in a good place to identify more accurately the resources that you might need, and also how we utilize engineering CAD tools and models to further conduct trade-off studies for both the design and the operational effectiveness of the system. All these activities, of course, are come with appropriate reviews, but normally you do want to have major reviews at these milestones of finalizing the conceptual design, the preliminary design, then the detailed design, and also we'll talk about reviews to discuss testing and validation results and things like that in chapter 6. So let's start discussing an example of a documentation tree for a complex system, a complex project or product. We discussed that we have a program management plan that comes from program requirements, that most of those requirements are from a business perspective, and we acknowledge that in parallel with the technical part that we are focused on over here, this is the type A specification that we discussed in chapter 3, there is also a systems engineering management plan that ties into the program management that has to do with resources, budgeting, timelines, high-level marketing features interface. And we said we're not going to worry about that part. We are worried about the more technical and a specific enterprise of design at the system level over here. So we have that type A specification that we completed in chapter 3, and we also said that the specific outlines and sort of questionnaire aspects of them, as they come from Incosi, are very convenient. And the idea of writing documentation and specifications is not for the pure sake of just doing it. I mean, that doesn't really help anything. It is really to help you keep you on track and keep all the important issues in front of you and take you and guide you through the thought processes so things don't slip through the cracks, because in complex systems it just takes one thing. There are a zillion variables, and you just take one thing to derail the project, to make the system or the project and the program fail. So you want to make sure that you have some tools and processes to make sure that things don't fall through the cracks. That's all we're trying to do. So in that context, you want to make specifications and documentations as concise as possible. So as long as you can document that you have gone through the process and go through those thought processes of checking everything, that's what we want to do. And this documentation helps you with that. So we have, beyond the system or level of specification, type A, we have other types of specifications for which you have access to the outlines. They are on the book, and if they are not on the book, all of them, they are certainly in the Incosi website. So again, these are very succinct outlines that you can treat as questionnaires and essentially address every aspect of them. So the next one is type B, specifications that in conjunction with type, that is very much like type A, okay? And as well as type C. So those three are similar in the sense that they cover the same aspects of type A, but they're more specific to the system, the subsystem level, and they are more, they're easier to tailor and steer towards software or toward hardware. It could be, for example, that if you have, as part of the overall system, you need a test infrastructure or you need a test fixture, one of these specifications, for example, the type B could be used, or the type C could be used to specify the test equipment that you need and are going to use. So I have a slide next with some more details on these specifications. But type B and type C are subsystem and equipment level type specifications that have some similarities, and you can tailor towards the hardware or the software. A distinct departure are the specifications D and E. And type D is specific to the specification of processes. So instead of product or equipment or software, this one has to do with the specification of a process. For example, how do you assemble a product? How do you put it together out of different units? So the specification of that process would be detailed in a specification type D, so it lends specifically to that endeavor. And then the other one, type E, has to do with materials. So perhaps as part of your system, you need to specify the nature of a specific material. Perhaps you need a bonding agent, and that bonding agent has certain characteristics that you need to specify so it can be procured correctly. So anything that has to do with material, you would use specification E. So to kind of summarize, and going back all the way to specification A, which you're familiar with, we have the top-level technical performance, operational and support characteristics. Here you capture the results of your feasibility analysis, and after you understand the need, the operational requirements of the system, the maintenance and support concept. So we actually went through that a lot. The appropriate technical performance metrics, so as they would come from a house of quality analysis. The main functional description of the design and the system and the design requirements and the system allocation. So those things are captured in the Type A specification. And then, as I said, Type B is very much like Type A, but they are below the system, so it lends itself to subsystem types specifying. Then we have Type C, which again you can steer, and also this goes for Type B, you can steer towards software or hardware, but Type C is it lends itself to specifying things that you're not necessarily going to design, but you perhaps are going to procure off the shelf. And this is very important, and we'll talk more about this in the next chapter, but at every step of every system design, you have to be checking whether it makes more sense to procure something or use something off the shelf, something that exists, versus making it or designing it from scratch. So the idea is to choose the most appropriate venue and path for the success of the project and the product. So we're going to be discussing the trade-offs of making things from scratch, from the perspective of non-recurring engineering costs, a middle ground where you basically get something that exists and then you customize it for the needs of the system, or using something off the shelf. If you're going to use something that already exists, if you're going to buy technology, buy products as part of, or components as part of your system, then you still need to specify what you need so that the procurement is takes place correctly. So the Type C specification, whether it's software or hardware, lends itself for that. Then again, the Type D, so these are specifications associated with processes that take place as part of being bringing the system into being. But also, this specification lends itself to describe or specify technical requirements associated with services. Perhaps part of your system is an eco-infrastructure, and it's not just something software or tangible, but it requires a service infrastructure. This would be the specification that you would use for that. And finally, as I mentioned, Type E has to do with the specifying technical requirements of materials that are used in the process of bringing the system into being. Can I get a check, because I'm not seeing the Zoom control window. Can everybody still hear me well?
Yep.
All right, very good, thank you. Okay, so after you have put in place all these specifications, you are in a very good place to be able to identify resources that you need to deploy this function of bringing your system into being. And you have to recognize that this activity has three inputs that influence it, and you have, from a system design perspective, you have different levels of say or control over them. So first, we're going to recognize that we have certain external controls and constraints, and these ones we have really very little control over them. But we have to understand them so we can operate in that environment. And these are things like the technology that exists. We talked about that in the previous chapter, that you have to be very cognizant of existing technology so you can either develop it further, research it further, understand the constraints of what can be done technically. So that's very important. But there are other things. There are external political, sociological, economic, and environmental environments or circumstances. And normally there is very little that you can do about that. So from a technical perspective, the technology that is there is what is there. If it's good, you use it. If not, perhaps part of your system design needs to be, it is congruent with the budget and the timeline. Part of the system design is that you have to develop that technology further. Okay? Then there are other mechanisms that are semi-rigid. So you don't have total control, but you can lobby for them to change. And let's say if you are in a company, there are certain human resources available to you. There are certain support available to you in terms of human resources. So staff and technical staff and things like that. There may be certain materials that are available for the system design, computer resources in your company, the actual facilities, the laboratories, the offices. Again, what type of maintenance support do you need? I mean, you need people that take care of the copier. You need people that keep the offices organized. And so you need all these mechanisms, and if you need something beyond that, you may be able to affect some changes, but they're sort of external to the actual system that you are trying to put together. And then these are the main things that come out of your analysis from a specification perspective. These are the real inputs to the function of bringing the system into being. So those are the requirements, the actual organizational structure that you have identified as needing to bring the system into being, specific raw materials, all the data that you have collected so far, and the documentation that we have discussed. So this you have put together. But as you bring the system into being, you have to have a step, a check, to contrast what your system requirements are as an input to the function of bringing the system into being, in contrast to things that you cannot do anything about and things that you may be able to change somewhat, and see how they stack against each other, and either try to change some of this, or recognize the limitations of this the environment where you are trying to operate, and adjust your inputs accordingly before you go into the function of bringing the system into being, so you can be successful. And once you do that, then you can go into that function, and of course the outcome of that is your system that is ready for use and being supported, and perhaps some ways. So this is kind of a conceptual call to action during this process of checking what you have at this point, after you have done all the documentation and specification, against the realities of where you operate locally and where you operate globally. All right, so this is a chart, and many times, or I would say sometimes, I have very busy tables or charts like this. These are not meant for me to read it to you because they are in the book, but they are here for me to remind myself and stress that you do spend some time studying the specific table, the specific chart that I showed to you. So I would like to highlight this one, that it shows a number of specific and important activities that we have discussed in chapters 3 and now 4, because some of this, like the need identification, we discussed in chapter 3. But this table spells out still in a very concise manner, but it's still more wordy than what I want to cover in a PowerPoint presentation. So it specifies the required inputs, what the expected outputs are, and what are the resource requirements. So this is a good chart to have because these are some of the main activities that we have discussed in chapter 3 for conceptual system design, and that we are discussing in this chapter for preliminary system design. So I want to make a call to action to you to spend some time, read and study this table. Okay? And again, if there are any questions, then you can bring him at the beginning of the next section, of the next session, when I ask if anybody has any questions. Now let's look at how this function that we showed. Okay, so this is a detail of this box over here. How this function of bringing the system into being may look. And again, systems are can have infinite variations. I don't know what system we may be designing in the future. I don't know the specifics. So, of course, it is not feasible for me to cover this specific system, but what we can do is come up with some general example, so it's not so abstract. So some general example that gives you an idea. Something that fits something, that would fit most systems that you may be involved with. So here we have this the life cycle of bringing the system into being for a system that may have 3 parts. It may have a hardware part, it may have a software part, and also many systems will have a human interface or human experience or user experience part. During this sub-life cycles of development, we are going to be keeping in mind the waterfall model of coming up or transitioning from the system requirements analysis all the way to the type A specification and the feedback loops that are involved in the different activities that we discussed in chapter 3. So this is something that we did before, and now we have this not only the type A specification, but also the other type of specifications, and we're ready to start looking at how they are going to influence and how they're going to dictate the specifics of the function of bringing the system into being for each of these three parts: hardware, software, and the human part. So for that, you will start with your, you have a reference of what that hardware needs to look like, and you're going to be doing your preliminary system design, which we'll discuss in this chapter. And then what we're going to see later on is that you're going to go into your detailed design and the actual development of anything that is hardware, equipment, the units, the assemblies, the modules, parts, everything that has to do with hardware. And you're going to eventually come up with prototypes, okay, for the hardware. On the software side, you're also going to have the reference specifications, and then you're going to be able to write software requirements and analyze them. And you're going to do your classic, so this one shows classic a software development cycle with preliminary design, detailed design, the coding and unit coding and testing and integration, okay, so of the software. So this is a classic approach as opposed to, let's say, an agile approach. And then, as important is the human part of it, which may deal with the human interface, the human user experience, any services that may be part of the overall system, and also the maintenance and support that we captured by specifying a maintenance concept. So all that really deals with people, and they are all further analyzed here and further designed here. So they go through their own design flow, and you may, for example, end up with some mechanical look-like type mock-ups of the system, so you can test how humans interface with it and testing the ergonomics of it. Normally, the people involved with this function are industrial engineering people, and also people that are not even engineering. They have degrees in human experience and cognitive sciences and things like that. You actually don't want engineers to do this because we are too pragmatic. So, but there are people that are very good at doing this, and you need to identify them and rely on them. So when you have prototypes for the hardware, the software, and some type of good idea of the human interface part, then you can start integrating all those in an overall system and start evaluating it. And we'll talk some more about that in chapter 6. But this gives you sort of a big picture of what comes next, including the detailed design activities that we talk about in chapter 5. Okay. So part of this preliminary design, a most important activity that we started in chapter 3 is the packaging of the major elements of the system into logical and physical units. So this type of diagram, which is again an example, some system, but I want to go through it as an example of how you can use this functional diagram to sort of package a system from a logical and physical perspective. Once you go through this, many times the physical packaging will coincide with the logical packaging. And that's actually a good thing. that's actually a good outcome. So let's say that you have a system X, Y, Z, and you start by trying to understand from the system requirements what is the operational activity of the system. So, for example, this system has 3 operational modes, and you use these connectors or and connectors to start aggregating the operational functions and so functions of the design, so you can package them together as they make sense. So this system is going to have 3 operational modes, so it can be in operational mode 1 or in operational mode 2 or in operational mode 3. And then you identify what are the operational functions in each of the modes. Well, let's say the system, when it is in operational mode 1, whatever that is, and again, this is all made up, so I don't know what system this is, it's just an example. So let's say that this system, when it is in operational mode 1, it has to have functionality to determine bearing information, tone information. It's going to have a control function, and it needs to have a self-test capability. Then when it is in operational mode 2, it is going to have to determine also bearing information, tone information, range. You have to have a control function and also self-test. And then operational mode 3 is going to determine range information. It's going to have to do transponding, which is transmission and receiving. It's going to have a control function and also self-test capabilities. And then you start looking at the sub-functions as appropriate. So let's say that the bearing information needs to have a bearing alarm functionality, again, whatever that is, and azimuth signals identification or processing, and needs to identify or verify the bearing validity. The tone, it needs to identify a tone, and it has some tone volume functionality. The range, it needs to process the range signals, validate the range signals, has some alarm depending on the range, and it needs to measure the range. So I mean, if I had to guess, this is some type of radar unit, but again, that's not what's important. Then the test, the self-test function has a continuous self-test, so perhaps you have a mode that the system is continuously self-testing just to make sure that the system is operational at all times. And it has perhaps an interrupted self-test, which it interrupts functionality every so often, and it does a more comprehensive self-test. And it also has a go, no-go indications, perhaps on power on. And again, these are AND connectors, meaning that they're all required on this, these sub-functions are all required in these functions. Then you have this transponding, which has reception and transmission. And then you have the control function that has power in there and channel selection, it controls the modes of operation, and so forth. Okay? So now we look at how it would make sense to package all this functionality. So here we have that we could say that the range and bearing functionalities, and notice how tying them up here, it gives you a pictorial view, I mean, if you count, if you look at, you know, what modes are using this functionality. So here we can say we're going to put the bearing and tone and the range, we're going to package it in this unit A. So we can make that, again, in the context of the system. So that has to be informed, of course, by the context of the system. So you would say, okay, unit A is going to have all that functionality, so that could be a board. And we said that it has to have self-test as well. So the self-test is going to go in there. That is going to have that functionality. Then unit B is going to be the transponder. So this is going to be a communication module, which also has the self-test functionality. And then unit C is going to be the power and controller, and also has to have the self-test functionality. So you may, this system, you may package it in, this looks very much like some type of hardware system, so you can package it in 3 boards. You know, one board is going to be, this looks like a radar type board, this is like a communication transceiver type board, and this is the controller of the system. Okay, so this may have a microcontroller and also the power generation for the overall system. So it gives you a nice way of looking at macro functionality and sub functionality and try to aggregate it as it makes sense in the context of the system design in a specific functional packaging, which actually translates also nicely to physical packaging, because I did mention that these 3 could be 3 distinct boards. So this is an important part of the preliminary system design activity, to use this diagram to do the functional packaging. Furthermore, this functional packaging allows you to budget and trace different aspects of the requirements of the system and allocate them to different units. For example, the same system at the top system level, you may have a cost, you may have certain system availability, and you may have certain reliability requirements or mean time between maintenance. So you can start allocating that, even things, for example, like size and weight. So if the overall system is to cost 50,000, then you can start allocating the cost to the different units, and you know that the addition of these 3 cannot be more than 50,000. Same with the weight. If you are allocating the weight and you have a weight budget and size budget for the system, you can allocate that and trace it back to the overall system requirements, and also even do that at the sub-assembly levels. You know, I said that these things were boards, but maybe they're boxes, and each one of those boxes have their own boards. So the idea is that you can allocate cost, weights, and physical requirements, as well as reliability requirements. So noticing that, and the idea of this course is not to go into the quantitative aspects of reliability analysis, but I will tell you, for example, that if the overall system has this type of availability or reliability level, then each unit has to have a much higher or better reliability and availability level than the overall system, because if one of these fails, then the whole system fails. So when you aggregate it through reliability statistic analysis, which again is not the subject of this course because it's not quantitative in nature, But the book does deal with that in subsequent chapters. You should keep that book as a reference. And remember that we're just covering a very small portion at the beginning of the book. So the book does have a wealth of quantitative analysis and information in subsequent chapters, and they do go into quantitative reliability or statistics-based reliability analysis. And what you can find is that, as I said, if you have certain availability and reliability requirements of the system, the subsystems have to have a much higher reliability. So when you put them together, okay, they achieve that overall reliability level. Because if one thing fails, then the whole thing fails. So it's important to recognize that you can do this type of allocation and budgeting once you understand the functional allocation and the composition of the system. So as I said, this type of functional analysis helps you with the packaging, the reliability analysis, maintainability, all these factors that we have been talking about and alluding to. So maintenance and logistics support. Also, what is the manufacturability of the system, even how you dispose it, if that's part of it. And as we looked at financial information, also economic analysis in the system. Which leads us into detailed design considerations, which we talked about back in chapter 2, that when you are designing at a system level, you are looking ahead and not just having just a few prototypes. That's not what we are after. We are after a sustainable way of executing the bringing about of a product. So you have to look at all these design considerations, such as that we have mentioned, so reliability, maintainability, safety, support and service, manufacturing, and of course the economic aspect. So it is important to tie this analysis through the allocation and budgeting to this detailed design considerations for the system. So this is just here to call to your attention another view of the same sort of an example of the evolution and life cycle of the development of a product. So basically here we have the hardware, the software, and the human element. So it's sort of the same thing, just a different view. And it has some more information here on the right. It is a again, this passes the threshold of business of diagrams, but it's here because I do want you to find this picture in the book and study it, and also it ties it to the different. It's an example of the evolution of the design, from system design, the preliminary design that the subsystem level that we're talking about, and then later on in chapter 5 we'll discuss the detailed design and development, system integration and testing, including validation and tests, chapter 6. But do spend time, and again, the assumption for me is that you're reading the book, because that's something that you should be doing. But I'm highlighting this as an important diagram to study in chapter 4. Now, as we conclude the chapter, let's talk about the place and usefulness of computer-aided design, modeling, simulation in the development of complex products and systems. You have different type of software products. We're mostly used to CAD, what we call CAD, which is software and modeling that you would use during the design phase. But more and more these days, these software systems are being used to virtualize beyond the design, the production and the construction of the product, and tie into it through single interfaces and seamless databases, seamless interfaces, and so you have a more comprehensive and uniform data and design flow from a computer-aided perspective. So, and you can see through the evolution of systems and functions, different companies are bringing these products to market to help with the design of complex products. So MathWorks is one of them. There's a wealth of different models and ways of coming up and tying into the production and the full life cycle of the product. So you're playing with System Composer, which would be like here, okay? But then, System Composer may tie into, if you were doing a radar system, for example, System Composer will tie into your phase array toolbox, which you can actually use to design your radar system, and that would tie into your DSP toolbox, which will further help you with the detailed design. And basically you could get all your C code and all your functionality and have software to embed in some type of hardware. So at that point, you transfer your detailed system design into an actual databases that can be used to guide the capturing of actual hardware. And let's say if you're using mentor tools and the valor flow, you could tie that hardware design, the schematic, the actual board layout, you could actually tie it into the manufacturing of the board, and then the software will go on the board. So you can see how all these software tools are being integrated together. And not only that, because once you have a board and a 3D model, that can tie into SolidWorks to make sure that the board fits the enclosure. So you're really doing a lot of virtualization of the system design before you even have anything that is physical, and that saves a lot of money, saves a lot of time, and that's why it's a good thing. So tools are just getting better at that, because the vendors of these tools have recognized the need in the marketplace for these tools. So we need to be cognizant of that and use them. And that's why I try to bring System Composer to bearing in this course as the initial place where you can start capturing requirements and simulating the quality of the capturing of the requirements. So this is kind of a summary of the things that I just said. So what can you do with software and models? Well, without having anything physical, you can look at alternatives in a short time frame, because you have to build anything, and you can simulate and verify the design for different configurations. So again, it saves time, is from a cost perspective is a low cost because you are not dealing with anything physical. You can look at design changes and different enhancements, but it is important to recognize that the data that you get is as good as the models that you use. So it is important to recognize that when you are using modeling, there is a spectrum of the time and that it takes you to develop the model and the accuracy of the model. So at one extreme, if you want something really, really accurate, well, you might as well build it because it's going to take you a long time to model something that accurate. So you can just build it and have the real thing. So the idea is to save time. So what you have to do from a system design perspective is to understand very well what is the right level of abstraction and what is the level of quality of the model that you need. That's very important to understand and understand what is the data that you are trying to obtain. So let's talk a little bit about that in the next couple of slides. But the model should represent what you're trying to study, the issue that you're trying to study. So there is nothing wrong with having partial models, whether they are mathematical in nature, equations, system of equations, or behavioral in nature. You can have models that just reflect the aspect and the issues that you are trying to determine. But the model should be comprehensive. So it should be all the issues that you're trying to capture and study, and also it should be reliable. So these bullets here are very important to understand how you go about modeling. So it should be simple enough to allow for implementation in the problem that you are trying to study, but it should be comprehensive for that issue. Okay? And then it should be expandable and reusable. That's important. Models should be designed for expandability and reusability. And you should have a repository of models for different functions, for different things, so they can be evolved and reused in the future. So let's talk a little bit about mathematical models that are specific equations or system of equations. What is attractive about them? For example, state space type of system of equations for systems, they are very, very attractive because you can model systems in terms of their state and how that state affects the outputs and how that state affects the next state or state transition in terms of the present state and the inputs. So that's a very nice infrastructure to understand system behavior and be able to actually model them through a system of equations. It also translates to behavioral models through a state machine expression of the system of state equations. So, and again, they are just equations. In software, you can look at all the relationships of different states. You can compare different solutions for them for the state for the system, and mathematical models give you clear cause and effect relationships. So again, a state versus output, next state versus inputs and present state. These are equations that give you direct causality between the outcome or outputs and the inputs into those equations. And you can also collect data, and if it's an analog type model or equation, you can collect data to validate the model, and then you can use that to predict different situations. So if you design an experiment correctly, so let's say that you have some process that the outcome is some time and temperature, and the input is coming from two temperature sensors and also a flow meter. Now you have three variables, and you can construct or design an experiment, take data, and then construct a surface equation with those three variables, and that can give you or a state or a space equation with those three variables, and you can look at outcomes for any specific or range of inputs. So you can construct with discrete data points, you can construct a model, an analytical equation-based model, and then use that equation to predict any other types of inputs or ranges of input. It also can help you with the analysis of identifying areas of risk and uncertainty as you go through the process of modeling. So all these are good practices in the preliminary design of systems. So what would a genetic system analysis process from the modeling perspective would look like? So the most important thing, recognize that we start with the requirements. So again, it's very important to have good requirements because that informs everything downstream. And again, we have discussed a number of different specifications for these requirements. Then as you go into your system analysis, it is very important to define what the problem is, what are the goals of this analysis, and you may have many different analyses as part of your preliminary system design. So, but if we just take one at a time, you can define that problem, define the goals and the constraints, the ground rules, and the different alternatives that you're going to investigate, and how you're going to approach the different solutions. Then you have to define and identify how you're going to measure. How you're going to measure success, how you're going to measure, or basically what is the criteria as you compare different approaches and alternatives, how you're going to measure them and contrast them against each other. What is a good alternative? What is a better one? What is an excellent one? You have to have very clear what those criteria are, as well as the variables that you can change, and the variables from input perspective, from output perspective. What is the data that you need to get out of this modeling exercise? So you need to identify all of that, and also in the context of if the activity lends itself to identify risk and uncertainty. For example, identifying variances and sensitivity of one output with respect to one input. You can measure that. So essentially, you can also, as part of your analysis, measure how sensitive your output is to a specific inputs. And that's mathematically, that's the partial derivative of that specific output with respect to the partial derivative of that specific input. So you can actually analytically quantify that. And that's where you get into identify what are your evaluation techniques, from a mathematical perspective. There are many of them. And again, the course here is not to go into the specific, just bringing up that there are many ways to go about it, okay? Now, a lot of the tools that you buy, from MATLAB, the value that they're bringing is that you don't need to know how to do any of this. They're doing this for you, okay? So you don't need to know anything about queuing theory, for example, okay? If you're using a network toolbox to try to model quality of service, you don't need to know anything about queuing theory. They are doing all that, okay? Or you don't need to know anything about linear programming, okay? They are doing all that analysis. So that's where that's what they are selling you, that expertise expressed in their software, okay? So then the next question is, do you have all the models that you need? And let's just say that you do. So you start running the model, and after you have constructed your system in that environment, so you'll see that in MATLAB you capture diagrams for your system. You capture diagrams in Simulink for your system. So you run your model and you collect data. Okay, for all the different alternatives that you want, to collect all the data that you want, and then you put that data in such a way that it allows you to analyze it. But the idea, so the tool is not going to give you the answer. This is where the system knowledge comes in, as you have aggregated by looking at all the requirements and specifications, and you can look at what recommendations do you make, how confident are you of different things, how the trade-offs look against each other, break-even points, you're looking at different cost analysis, and as I mentioned, sensitivities which deal with risk and uncertainty. So you get all this data and you can start making informed decisions about the system and take appropriate actions. If you sometimes this action has to do with changing the requirements and going through the loop again. And sometimes you don't have a model and you have to actually construct the model. We talked about that. So, but again, there are I'm very partial to MATLAB, so I think that they have the most comprehensive set of models already ready to use. And but there are others. There's COMSOL multiphysics that basically you can couple electrical models, mechanical models, all kinds of different models together and do simulations. But again, so does MATLAB. They do have, and there are other tools as well. The nice thing about MATLAB is that they're getting into the system level. So you can start with something like System Composer and keep using MATLAB for everything down to the very detailed design, because they're coming from the detailed design part of it. If you were using, there are many tools that do only the system part, but then that's where they stop. It's just a system level. So I'm glad that MATLAB is getting more into the system level design requirements, capturing, and simulation. And finally, as an example of how, of the applicability of models and how wide it is, again, this is an example. I don't know what this is. I don't know what project this is or system it is, but you can simulate and get data on logistic support factors. So you may have a logistic support model, where you have system operation, repair, the cost of the life cycle, inventory of spare parts and personnel required, a model of the equipment and the shop. So, you know, the model, the good thing is that it's all virtual, is all software, so you have a lot of flexibility. And you can get all kinds of data. You know, you could get data on you know, the logistic effects and the costs as the program progresses, and the cost of the support of the factories. You can look at the cost of different repair policies and compare those. You can look at and measure the rate of readiness, let's say, versus how much you spend on spares and inventory. You could look at the maintainability versus the reliability. So for different reliability levels, which is more reliability is more expense of the product, it's more expensive product, but you can look at how that affects the maintainability. But the maintainability also has a cost. So that would be a sort of a break-even point analysis. So you pick a reliability level that has a maintainability that if your goal is to break even, that you break even. You could look at the cost of built-in self-test capability. So of course, the more capability you have in self-test, that also is going to increase the cost. So you can look at that effect. Different costs of different test methods, manual, semi-automatic, automatic, because people are expensive and you're going to include people, the less automatic you are. So this is just an example, some made up type system, a logistic aspect, but just to give you an idea of the type of data that you can get. So don't think that you don't, whatever your questions are, whatever your data needs are, you can get it. You can always do a model of what you're trying to get, and you have to have that mindset. What you cannot do is arbitrarily choose. You need to be data driven. And the best way is and the least expensive and the most convenient way is through modeling. You need to be data driven. What you cannot do is make arbitrary decisions, shoot off the hip, and just go with gut feel, because these systems are too complex, and the chances of you getting it, your arbitrary answer being right is pretty much zero. So this is the end of chapter 4 on the aspects of preliminary system design. So basically it presents further activities that we do at the system level, and also highlighting how these activities are also done at the subsystem level for the system. So I'm going to stop here and then go back to the Zoom function to see if you have any questions, or if anybody has written any questions in the chat box.
I do have a really quick question.
Yeah, go ahead.
This is just regarding Canvas notification we got about the submission for PDFs. Is that just particularly pertaining to the Project 2 submission?
That's to that pertains to everything. So I'm sorry. Okay. I apologize. I changed my mind. This is a I found that. So basically, I learned how to use Canvas better. Okay, so I found that I could actually organize things really nice with the Canvas submission. So everything, including the homework. Let's say I'm going to assign homework today for this chapter, so it's going to be due by 7:30 a.m. next Thursday, and I'm going to sign that later today. So that's going to be done via Canvas. It needs to be submitted there before 7:30 a.m. and Canvas captures the time when you submit it. So yeah, it's everything.
Great, thank you. Thank you.
You're welcome. All right, so let me see. Any other questions, by the way?
Professor.
Yes.
Can I ask a question regarding the project? I know you were asking questions about that earlier, but my audio wasn't working at the time.
Yeah, no problem. Let me go back to the Zoom. I'm in presentation mode now. Let me go back to the Zoom. Yeah. Let me. Yeah, go ahead.
So this is regarding part F on project 2. This is for the documentation of the functional analysis for the system. So I understand the component of that is the functional block diagram that is part G. But there's also a few other flow diagrams that are talked about in the book. And I was wondering if we should also do some of those flow diagrams as part of that documentation. Or if we can just answer kind of like the questions that are necessary for that part.
So I need a block diagram. Just one block diagram would be okay. At the system level, it needs to be the type of block diagram that System Composer wants.
Okay.
So that's what part G specifically of the project is for you to go into MATLAB System Composer, draw the and if you did project 1 and looked at the videos of System Composer and all that, you should know which one it is because it only supports one. So this is for you to do it in MATLAB and simulate it in MATLAB and give me that documentation or integrate it into your report.
Okay. But other than that, you don't need any other flow diagrams or anything like that.
That's correct.
All right. Thank you.
But that's just for G. I mean, there are other diagrams through, from A through G, there are other diagrams, right?
Yes, there's the house color diagram.
There are other diagrams. I'm just talking about G is one specific MATLAB diagram.
All right, but then in addition to that, in part F, there's talking about the functional analysis.
Yeah, that's a different diagram. I do want that diagram.
Okay, so you do want the flow diagram for that.
Yes, of course, yes.
Okay, all right, thank you.
Any other questions regarding, the project or anything else? All right. Well, very good. So we're going to adjourn at this point. And I wish you a safe, healthy weekend, and we'll be in touch next week. Okay? Thank you very much.
Hey, Professor, you can disregard my one email. I was having trouble getting into Zoom, but I got in. I don't know why Zoom was being annoying.
So basically, this can happen, guys. There is being a surge of usage. Some people have like a lot of hard time with Zoom. It can happen. We're sorry about that, but still Zoom is the best platform for this. But the servers are getting the capacity of the servers are getting tried. So you need to basically keep trying, and then. If someone at some point cannot join or anything, please do remember that I have my office hours, and I can essentially, if you have any issues, you can drop by the office hours and then we can talk about it. Okay?
Thank you. Thank you.
All right, great. Anything else? All right, everybody. So again, have a good weekend. Be safe and healthy, and we'll be in touch. Take care. Bye-bye.
Bye-bye.